So we're going to look at statistical modeling of MIMO communications channels. And here's a communication channel, a MIMO communication channel with input, a precoder, multiple antennas, and this is the MIMO, multiple input, multiple output, and multiple receive antennas, and then post-processing, and then you get your received value, and you're going to try and work out what the signal was that was sent to you. And for more information on this, there's a video in the link below on the channel. Now, H is a matrix, and we can write down this matrix equation, and it is all the channel gains between each transmit antenna and each of the receive antennas. It's a matrix of those gains. And if we're going to design a system, we would like to know how our system's going to perform, and to find that out, or to calculate that, predict that, we need to know about the channel matrix H. So what we could do is go out and measure every single channel that's possible in every person's house for their Wi-Fi in all the different rooms, and do a comprehensive measurement process and measure all the channels. And that would be very time consuming and essentially, of course, impossible for everyone's house. So what we prefer to do is to look at a statistical model of the channel. So what are the statistical models? What's a common statistical model? And I'm just going to briefly look at one of the main ones here. So one model is to assume that the antenna elements are all in omnidirectional antennas transmitting in free space out into a room where there are scatterers, and where there's a sort of a uniform distribution of scatterers all around. And in that case, the channel gain can be modeled as, and sometimes is modeled as, an IID, where this is a matrix. This is an IID matrix. It's a matrix because there's N transmit antennas and M receive antennas. So it's an IID matrix, zero mean, Gaussian, with unit variance. So unit variance, complex Gaussian with unit variance. And so that is one model that you can assume for the channel matrix. But we're going to look just now at one that's a little bit more practical and a bit more realistic, and think about how that comes about. So actually, let's think why it wouldn't be an omnidirectional. And the reason is because there are scatterers that are not uniformly placed. And a common situation, for example, if we look at a side-on view sliced through the ceiling of a room, for example, is a common situation in offices and other places to have a Wi-Fi access point mounted up near the ceiling and in the corner. Let's just take that one as one example. Of course, this is going to apply for any other sort of practical place where you put your Wi-Fi access point. In this case, you've got a wall to the side and the ceiling above, and often there's metal in the walls and in the ceilings as structures within the building. And that metal is going to form a particular properties around the way in which the electromagnetics radiate from that antenna. And so it's not the case that this is in free space in the open air, transmitting equally in all directions. If we look at this, we can of course see and think that especially if there's metal supports in the walls and the ceiling, then there's going to be instead of a circular radiation type pattern from this effective antenna, so it's an antenna placed in an environment, instead of that, there's going to be a sort of a preferential energy going out in this kind of direction. And that is not uniform in all directions. Same thing at the receiver. The receiver is often, the person is maybe in their laptop or sitting or holding a mobile phone close to their head, for example. And with the laptop, they might be sitting on a table, especially if it has metal supports, metal legs or so on, often the case in offices, for example. The metal in particular is going to affect the signals that are coming around it. So these scatterers around the transmitter and the scatterers around the receiver are having a much a bigger impact than all the other scatterers because they might be more diffuse for the other scatterers. And also these ones are sort of fixed in relationship to the transmitter and fixed in relationship to the receiver. They're not moving around like, for example, cars would be moving past or people moving past in the corridor or what have you. These things are sort of fixed related. And under this kind of assumption, then we have a more sophisticated model for our channel. And we introduced these two other matrices, these sort of correlation matrices, where these matrices here give us, and we put a little W underneath there, this is common, and there's references below the video to papers which explain this in more detail. But the S here represents the scatterers around the transmitter, because our H now is being formed out of three matrices. So there is still a matrix which is an IID zero mean Gaussian unit variance that represents all the scatterers between the transmitter area and the receiver area, and they are still modelled in this model. They're still modelled as IID zero mean Gaussian, but the scatterers that are around the transmitter affect this matrix S, a correlation matrix around the transmitter, and the scatterers around the receiver affect this matrix R, the correlation matrix around the receiver. And the overall effect of this is to give us a channel matrix which is complex normal, of size n and m, with a number of transmit and number of receive, which in this case is zero mean, although you could add in another matrix, a mean matrix, if there are some dominant paths for Rician, but just for the Rayleigh case, where this is the correlation matrix is R Kronecker producted with S. So this gives you a matrix which is complex normal with zero mean and this correlation matrix in this complex normal. And so this is a more sophisticated one, which is more practical, including the correlation around the transmitter and the receiver. And the final thing to say is how do you generate these, or how do you decide on these? This one here is obvious, it's clear, it's IID zero mean Gaussian unit variance. That's the way you can construct these in a simulator, for example, or do some calculations about it, capacity type calculations and so on. But what about R and S? How do you generate these? Well, one way to do this, and again in the references in the video below this video, one way to do this is to assume that there is this scatterer environment here that results in a shape which is a Gaussian shape in terms of the angle of departure and a Gaussian shape in terms of the angle of arrival. So for example here, we assume then that this has we can assume that this has a mean angle of departure. So this is angle of departure, and then that there might be a mean angle of arrival, which depends on the walls, not just the table where the person is, but the walls and all of the scatterers that are in the close vicinity of the receiver. And then we would model that as for the angle of departure, for example, we model it as a Gaussian angle, where there is a mean to that Gaussian angle and a variance to in this case, the transmitter T, the variance to the transmitter. So we'd have a Gaussian for the transmitter and a Gaussian for the receiver. And under that assumption, there are formulas for calculating R and S. I'm not going to give those formulas here in this video, but if you follow the link for the papers that are referred in the information notes below this video, you'll find them there. So I just wanted to give this as an explanation as to why you have in some cases just a channel model that's IID, and in other cases you see these correlation matrices either side of the IID when you're looking at MIMO communication channel models. So if you found this video helpful, give it a thumbs up. It helps others to find the video. Subscribe to the channel for more videos, and check out the web link in the information below this video where there's a full categorized list of all of the videos on the channel.